So, can you see my screen?
Yes.
All right. So let's continue our trip to the various properties of angles and stuff. So, can somebody remind me what we talked about last time regarding angles? So, what kind of angles did we talk about?
We were talking about complementary and supplementary angles.
Okay, can you remind us what this is?
Complementary is an angle that adds to 90 degrees, and supplementary is an angle that adds up to 180 degrees.
Yes, but careful. There have to be two angles that are complementary, right? So we would have one angle x and one angle y, and those are said to be complementary, for example. Right? So there have to be two angles to call them complementary. But yeah, the idea is that they sum up to 90 degrees. Yes, Naomi with an amazing profile picture is telling us about obtuse, acute, and right angles. Acute and right. Yes, an obtuse angle is greater than 90 degrees, an acute is less than, and a right is exactly 90 degrees. Perfect. Okay. The supplementary angles are two angles that add up to 180 degrees. Very nice. Any other angles that we talked about? There were a couple of more. Like, what if I bring two lines? Then what are those angles called? Anyone, you can unmute and tell me, or you can type in the chat. Corresponding, you're saying we did talk about corresponding, but these are not called corresponding angles. These are called, actually, these are the
Interior.
opposite angles. Not yet. The interior angles we're going to talk today, actually, in more detail. We talked about these are the opposite angles that we talked about. When you take two lines and you cross them, then there are four angles formed. And each pair like this is called opposite angles. Okay, so these are opposite angles. X and Z are opposite angles, and they are actually equal. That's what we showed, right? So the angle X is equal to line Z, and the angle W is equal to angle Y. Okay. All right, and Naomi mentioned corresponding angles, and for the corresponding angles, we talked about two parallel lines, and then we cross them with another line. So vertical angle. We didn't talk about vertical angles, and I'm not even sure there is something like that. This would be called 90 degrees angle or right angle. Those we are saying that this and these are vertical then, if that's what you're referring to. So we talked about corresponding angles as well, and they happen when we take two parallel lines and we cross them with another line. Then there are these patterns created. So there is this Z pattern that is created, and then these two angles are equal. And actually, let me show you the idea. Yes, here are the patterns. So when we take two parallel lines and we cross them with another line, there are these patterns created. Okay, and what is important to remember is that the Z pattern is the most important. These two angles that are formed under the shape of the letter Z So this and this, they are equal. Okay, and same goes for the F pattern. These two angles are equal. Okay, now for the C pattern, these two angles are supplementary, so they add up to 180. Okay. So, but this one is the most important that you need to remember. The Z, when you have Z pattern angles, they are equal. Okay. So more or less, this is what we talked about. And let me erase this. So now we're going to get into the, before combining all of these ideas together in a couple of problems, we're going to talk about the interior angles of a polygon. Okay. So by interior angles of a polygon, we call all of those angles that are formed inside the lines of a polygon. Okay. These are called the interior angles. Any shape you make and anything you can think of making, it has all of these interior angles inside. Okay. So what we're going to try to figure out now is what is the sum of those angles. Okay. So of course, if I give you any random shape, those angles can be very, very, very different, right? But their sum, we're going to see that is actually the same for a specific number of sides of the shape. Okay. And actually, let's see this with a triangle. So you just as a poll, tell me if you have seen this generally, that the sum of the angles of a triangle is 180 degrees. I don't think I asked specifically if you have seen this again. So have you seen this again in any previous classes? Okay, Naomi saying yes. Anybody else? Arman says that he has seen it last year. Okay. All right. Okay, so we basically show a kind of intuitive way to figure this out. Okay, so we just split the angles of the triangle like this, and then we see that if you rearrange them, in this shape, there is an angle of sorry, there is a line formed. Okay, and the line is an angle of 180 degrees. Okay. All right, so this was an intuitive way to see it, but what we want to try and do is we want to try and prove it. Okay, with all of the discussion that we made about the corresponding angles and opposite angles and anything like that, we want to try and actually prove this, because this thing with the shape that we did, it is nice to see intuitively. We believe that the sum of the angles is 180 degrees, but this is not a mathematical proof. Okay, and we're going to try to just formally prove this now. Okay, so to start off, we're gonna draw some lines. Okay, so I am just drawing some parallel lines. Okay, I'm drawing this parallel line here. I am basically extending all of the sides of the triangle. Okay, and I bring this line here is parallel to the base, to BC. Okay. So can somebody notice maybe some angles here that I can use if I bring this parallel line? Are there any special lines that we discussed, any special angles formed that we discussed? Okay, Naomi very quickly says the C pattern, but there is the C pattern, yes. But let's see, B to A and C. So like this, Naomi. Well, the C pattern in this case would be this letter C right here. This would be the C pattern, but there is an even better pattern formed. the most important one of the three, but you're on the right path. So
I can see a Z pattern.
yes, there is a Z pattern. Thank you.
Because if you go from left of the A and you're going toward the A, then you're going diagonal, and then you go right of the diagonal line going left. And
Yes.
that's a Z pattern.
Perfect. Thank you. So let's see. Yes, so there is a Z pattern happening here. Okay. And let me change the color of the pointer so that you can see it better. The Z pattern is right here because we have two parallel lines. Okay. And there is this angle formed between them. Okay. So this angle here is equal to what angle because of the Z pattern?
A.
A is this one, right? But where are the equal angles in a Z pattern? Yes, Naomi is saying B because that's the reason why we call it a Z pattern, because the equal angles are the ones that are resting inside the two angles of the Z. Okay, so actually this angle is equal to this angle right here, the inside angle here, this one. Okay, by the Z pattern. Okay, so yes, and the other side of A equals C. So there is another Z pattern happening right here. The Z is looking the other direction, but it's the same idea. Okay, so this angle is equal to the angle C here. Yes, in the shape that we have created, this angle D is equal to B, and this angle E is equal to C. Okay. So why have we done all this? Now, what can we notice about the sum of the angles of the interior angles of the triangle? Can we rewrite it in another way now that we have new angles? Yes, thank you, Naomi. That's the idea. You see, since the angle A, the angle B is exactly equal to D, and the angle C is exactly equal to E, I can just rearrange them. I can just use the other angles. So I can write A plus D plus A. Okay. Right. But as Naomi is pointing out, this is exactly a straight line. Okay. So this is 180 degrees. Okay. Very good. Nice. So that is an actual proof that we did. This is an actual geometric proof. Okay. And we took our intuition that we saw that those angles had to sum to 180 degrees, and we proved it. Okay, using actual arguments. All right, does this make sense? Yes, thank you, Naomi. Exactly. Yes. Okay, so does this make sense, guys? Did you understand the proof that we did here? Arman says yes. Naomi says yes. Anybody else? Does anybody have any questions on this, on what we did? Okay. So now what we would like to do is we would like to extend this idea to a bigger, to a more sides for a shape. Okay. So now since we figured out what is the sum of the interior angles for a triangle, the next step is to figure out what is the sum of the interior angles of a quadrilateral. Okay. So
right away, I can see a C pattern.
Wow, where?
So, if you start to the right part of the quadrilateral to the east, you can immediately draw a line to the top angle, and then you want to go down left, and then of course you want to go right.
Okay.
And that's automatically a
Yes,
C
okay, but
pattern.
let me ask you something. That is a C pattern, but not exactly, because how are you sure that this line and this line are parallel to each other? How can you be sure about that? because we discussed that these patterns hold when you have two parallel lines and you cross them. But here I never said that these lines are parallel, right? I never said it, and as we discussed, you cannot say they look parallel. This is not an argument. This is not convincing, right? So you cannot be sure that these are parallel, so you cannot be sure that this is a C pattern angle. Okay. But it was a nice observation. But be careful. If something is not explicitly given to you, then you cannot be sure that that just by looking at it, it is parallel, for example. Okay. And this is exactly what we did here when we started this proof here. We brought specifically, we draw the parallel. We said it. That's why here we had the patterns. Okay. Right. So yes. Okay. Naomi says that if we had a square, she says, then it would be simple because all of these angles would be 90 degrees. Yes, that is indeed the truth. But here, of course, we don't have any parallel actually lines. We don't know if they could be, but we don't know it. So here's my question to you: can you think of any way that we can use the triangle result? That we can use the triangle result into this problem? Since we know that the sum of the interior angles for a triangle is 180, can we use it maybe somehow in this? It can be put into half, says Naomi. Okay, I like it. Okay, how do I split it in half? And they are triangles. Nice. So I can just bring this line here, and then I have two triangles. Nice. Okay, very good. All right. So now that we have two triangles, we see that the sum of all of the angles that we're looking for is the sum of all of these smaller angles, right? And Ryan is saying that perfect. We have this triangle here, the sum of the interior angles. So this one plus this one plus this one, this is going to give us 180 degrees. Yes. And because this is a triangle, this one plus this one plus this one is going to give us another 180 degrees. So if we add them all together, right, we're going to have 360 degrees. So this is actually a very good idea. Okay, and we actually figured out that the sum of this random quadrilateral that we had is 360 degrees, the sum of the interior angles. Okay, very good. And we can extend this, right? We can extend this to bigger shapes. So
I can see that you can do three triangles here.
Yes.
So
okay.
that spot right there, if you draw a line to the opposite spot of the top of the pentagon,
Yes.
you could automatically form a triangle there. And then, of course, if you do it diagonally, you would form two triangles there. So you would have a total of three triangles.
Perfect.
And since
Very
both
good.
of them, well, I don't know about both of them, but the idea is that each triangle equals 180 degrees. So we might have to figure out what angles equal to 180 degrees.
Yes, actually, these three angles here sum up to 180, right? Because it's a triangle, right? Same goes for this triangle, same goes for this triangle. So the sum of all the interior angles is going to be 180 plus 180 plus 180, which is 540. Yes, thank you, Ryan. Okay. This process is called the triangulation, guys. This is when we take a big shape that has a lot of, that may potentially have a lot of angles, and we split it, and we try and split it into triangles. Okay. This is called the triangulation. And of course, there are a lot of ways to perform a triangulation. Okay. So this could be another potential triangulation, right? So try to answer this question for me. What if I used this specific triangulation? Would I still find the correct result or no?
The second one you showed, I don't think so.
This one you mean, that I have here?
No, like when you first presented the animation, like the first one, it was valid, but I don't think the second one was valid.
Like this one.
Yeah, this one is valid, but when you added
Mm-hmm.
the other one,
Mm-hmm.
it is, I guess it
You're
won't really
saying
add up to
it won't really
540.
add up. Yes, because here we have to be careful, actually. You need the minimum number of triangles on the shape. I like this idea, Ryan. That is a very good idea. You need a minimum number of triangles. Yes, as you can see, there are too many triangles, actually. But this will give us the minimum possible triangles. But let me just show you that we would still get the same result, okay? But if we were more careful. So the sum of the interior angles that we're looking for is actually the sum of all of those grid angles that I am making. Right? The sum of the interior angles of the triangle is only the sum of the green angles that I have put here. For the other ones, we don't care, really. Right? So in this case, let's count how many triangles we have. Okay, we have one triangle here, 2, 3, 4, 5, 6, 7, 8, 9 triangles. Okay, so that would give us a total of 9 times 180 degrees, which obviously is wrong, right? Because that's too much. But what if I subtract all the extra angles that I have? Right, so which of these angles that are formed here I don't care about? It is exactly all of those angles. So let me show you better. Let me change color to show you. These angles that are formed, I don't care about. Right? These angles I don't care about because they aren't the interior angles of the polygon that I want to find. But what is the sum of those angles? Can anybody tell me? Of those 4 angles here, what is the sum? 360 says Naomi. Yes, this is a full circle here. This is a full circle because it's going all around. So we have 360 degrees here. Right? Same goes for this one. This is another 360 degrees. And same goes for this one, another 36 degrees. So what if we just subtract all of those from the shape, right? Then if you perform this calculation, we can actually make a nice, so we can split this 360 to 2 times 180. And we would have 6 times 180. This is just algebra, okay? I'm just calculating. And we still get the same result, which is 540. Okay. So as you see, the triangulation doesn't matter. Yes, 9 times 180 minus 360 times 3. Exactly. Exactly. If you perform this calculation, you will get 540 degrees. Okay. So as you see, the triangulation doesn't really matter. We just have to be more careful on which angles we really need. All right. But I like what Ryan said. Ryan said we need the minimum number of angles, of triangles, the minimum number of triangles that we can create. Okay. Okay, so let's try to calculate the sum of this, the interior angles of this shape here. Does anyone have any nice triangulation that we can use?
Can I say something?
Yes.
I think if you like cut off the corners, like all the corners.
So like this.
No, I'm saying like the corners of the star.
Like this.
Yeah, and you'll, yeah,
Okay.
and like every single corner.
Mm-hmm.
And then you split the center with like 2 lines from like the bottom two to the top one, and you'll create.
Nice.
Yeah.
Yes. Yes, that is a perfect triangulation. Thank you. Amazing. So, and as you see, all of the angles that we need are right here. Right? All of the angles that we need are right here. All of them. Okay. Which means that all that we have to do is we have to count how many triangles we have. Okay, so how many triangles do we have here? How many triangles are created like this? Yes, now Miss telling me 5 times 180. Let's see. 5 times 180. Why 5 times, Naomi?
I realized the middle one can be classified as a pentagon, and we already know that or a 5-sided figure, so we know that that's
Yes.
540. So we don't need
Okay.
a triangle of that.
Mm-hmm. Nice. So what you did is you just calculated the rest of the triangles, and then you add up this middle piece that you know is 540 because it is a pentagon. Very good. Very nice. So we have this pentagon which is 540. Essentially, if you don't see, you just count that you have 3 triangles here, and then we have the rest of the triangles. So this should be 8 times 180, right? Which is 440 or 340. Yes. Okay. So so at the end of the day, let's see what we noticed. Okay. Let's see what we noticed. When we had a triangle and it had three interior angles, then the sum was actually 180 degrees. When we had a quadrilateral, it had 4 interior angles and we had 360 degrees, which is 2 times 180. And actually, it had 3 sides as well. That's what we're interested in. Okay, so then we have the pentagon, and the pentagon had 5 sides. And we found that the interior angles were 3 times 180 degrees, so it's 540. So can you see the pattern here? If I gave you a random shape with n sides, how many would we logically say that are the interior angles? Can you notice the pattern?
180.
180 times what? Because in all of the cases, we have 180 times something.
N minus
So
2.
N minus 2, yes. So if you notice here, we have 3 minus 2 times 108. And here we have 2, which is actually 4 minus 2. Okay. So it would be logical to say that a shape with n sides has n minus 2 times 180, the sum of interior angles. And this is actually correct. Okay. This is very logical to say. And the proof for this is kind of all the process of triangulation that we did. If you take any shape, if you are able to split it in the smallest amount of triangles, as Ryan said, and then you just add up all of these triangles, and you just have to be a bit careful on which of these triangles you really need. If you don't need some of them, you can just discard the ones that you don't need. Okay. So this is more or less the proof intuitively. But yes, we immediately at the end of the day, this holds. If you want to find the interior angles of a polygon, the sum is going to be n minus 2 times 180 degrees. Okay. All right, and actually, I'm out of time. I wanted to do some exercises here, but I think that that's better if we just pass into Gray because she also has some very nice things to tell you. So I'm actually going to stop here. Okay, and am I still sharing her? Yes. All right.
everyone.
So that's all I wanted to say. Okay, go on, Gray. Yeah. Have I
Hi,
stopped sharing?
Gray Carson. What?
Have I stopped sharing?
Yes, you have. All good. Okay, let me share my screen real quick. Let's see, this got closed down. Give me 1 second. Okay, can y'all see that? Okay, so we're gonna be talking about Pythagorean theorem, which is really exciting, you know, do with triangles and stuff like that. Before we really get into it, we're gonna do a little bit of a review, just to make sure we're all on the same page. So we're gonna be talking about square roots. So how comfortable is everyone with square roots? Like a scale of 1 to 10, like how are we feeling about that? All right, so people pretty comfortable. We're gonna do a little review for the people who might liking the answers. Okay. So we're gonna first look at like the physical, like what does this look like? And then we might be able to get into some more like numerical stuff. So if I'm talking about like the square root of 9, for example, we can actually represent this like as a square, right? So you see here, we have 9 boxes. Let me draw real quick. 9 boxes, right? 1, 2, 3. We have 9 of them here. We can arrange them into a square, and that has 3 on each side, right? So we have 3 and 3. And so the square root of 9 is equal to 3 because it looks like a square. And so if I were to take like the square root of 4, then I have we can take 4 dots, turn that into a square. See how there's 2 on each side now. So there's 2 here and 2 there. Square root of 4 is 2. So that's kind of what they look like. Let's look at it numerically now. All right. So here's like the symbols, right? We have the radical symbol, the radical sign right here. And then we have the radicand, whatever's in the radical. So here's like the formula. The square root of x equals a, then a squared equals x. So we just said that square root of 9 equals 3. So that means 3 squared equals 9, right? So this would be our x, our a. Here's a squared equals our x. Square root of x equals a. And we can do this with other things, right? So like square root of 4 equals 2. Then 2 squared equals 4, right? Works both ways. Now over here, you can see we have that the squared will cancel out the square root. So if we have like the square root of x and we square that, we're just going to get whatever's inside there because this symbol and this symbol cancel each other out. And that can go either way. If I have the square root of x squared, again, this symbol here cancels out this symbol here, and it's still x. So that's enough definitions. Let's get into some examples. So what about this first one?
May I
You
try?
wanna... Yeah, definitely.
It's 2
Awesome.
because 2 squared is 4.
Perfect. Yeah. All right, what's this next one?
Can I try again?
Sure.
25, the square root of 25 is 5, and 5 squared is 25.
Perfect. All right, I'm seeing some people in the chat for the last one are saying 4. It's correct, because then 4 squared equals 16. All right. Everyone good about that? Feel good? Let's see. All right, this isn't too bad. We have some more here. You want to just do this real quickly?
Can I try?
Anyone wants to get on the mic? Sure.
The square root of 36 is 6 because 6 squared equals 36.
Perfect. See, I'm seeing some people in the chat with some answers. So we have 8, because 8 squared, 64 equals 9, right? It's 9 squared equals 80. We're not going to get a perfect square like that. We're not going to get a single number out of here. So we can break up the number inside the square root, and then the square root can break up with each number. So for example, if I'm taking the square root of 20, what are the factors of 20? Could somebody give me two numbers that multiply to get 20?
10, 2.
10 and 2. All right. So we can break this up inside and say 20 is 10 times 2. And so then I can break this up, square root of 10 times the square root of 2. Or I've seen someone in the chat saying this also equals 5 and 4. And I like that one a lot because if we break this up like this, we can see that the square root of 4, which we already said is 2, right? So the square root of 5 times 2 now. So we can write this as 2 times the square root of 5. Perfect. I'm seeing people in the chat agreeing with me here. And then you see how, well, A and B, these are different numbers here, but we can also do the same thing with like the same number. So this would be for a perfect square. So if we had like the square root of 16, right, that's 4 times 4, right? So 4 times 4, then we can break this up, square root of 4 times the square root of 4. And if a 4 equals A, right, this would just be 4, because it's the same number there.
We're also going to have to deal with prime numbers, so it won't always have to be equal. For an example, like 20, you would have the prime number of 5 because 5 isn't divisible by anything by itself.
Perfect. Yeah. So we're talking about prime numbers, right? So we can, that's one way we could do it. We could break a number into its prime factors and see, how many, let's see, 4 times 4 is 16. Perfect. I've seen people in the chat. Yeah. So yeah, 5 is a prime number. We could break this up more. We could have said 5 times 4. And if you want to break this up into prime numbers, we could have broken 4 up to 2 and 2 because 2 is prime. And that's kind of how we break things up. So let's do some examples. All right, who wants to give this a try? Anyone who hasn't spoken yet, do you want to get on the microphone, help me out? Or anyone who has spoken, would you like to help me out?
I can try.
Awesome. All right, go ahead.
So you can split square root 15 into square root 5 and square root 3. Yeah.
Perfect, yeah. So 15 is 5 and 3, right? And so we got the square root of 5 times 3, that equals the square root of 5 and the square root of 3. And as Armin was saying, these are both prime numbers, and so we can't break them down anymore. What about 75?
May I try?
Oh, okay.
Sure.
So the factors of 75, we for a simple way, we can do 15 and 5 because 15 multiplied by 5 equals 75. And we could do the factors of 15, which will be 5 and 3, once again from letter A. Then we could put 5 on the outside because 5 squared is 25. The square root of 25 is 5. So we can put that as the outside the square root, and then we can put 3 in the inside of the square root.
Awesome. Love it. So does everyone get what just happened here? Because we have 2 5s on the inside, and so we can bring those 2 5s out as just 1 5. Because we're bringing them from under the square root to outside. So I think that's pretty cool. Someone's in the chat right here. Do you want to get on the microphone?
So 24 can be mixed up into 6 times 4. 4 is a perfect square, so that's 2. So we do the square root, which is 2. So it's 2 times square root of 6.
Perfect. Yeah, that was fast, but amazing. Look at that. So we have the square root of 6 times 4. 4 is a perfect square, so that turns into 2. So we could bring this around. 2 times square root of 6. All right. Perfect.
I think I've noticed something that's incorrect. So 6 multiplied by 4, I get how that's 24, but you might have to simplify 6, which will equal 2 times 3. And you're going to have the square root of 4, that's 2 on the outside, and the inside would be 3.
But 2 times, but that equals what that, so like 2 square root of 2 times 3 equals 2 square root of 2 times 3. 6, I meant, not 2 times 3. So what you're saying equals each other, I'm pretty sure.
Yeah, so I see both of your points. So we have square root of 2 times square root of 6. That's correct, but we can break 6 into 2 times 3 and 2, which you were saying. But if we were to break this all up, let me clear this slide if that's all right, so we can have some more space to think about this. All right, so we had 2 times the square root of 6. So this could be the same thing as 2 times 2 and 3. But 2 isn't the same as 3, and the 2 is already on the outside, so we kind of discard it from what we're doing inside the radical. These are 2 separate things. And so we have to leave them alone. So if we were to break this up before we extend it, right, into its prime factors, we have 4 times 6. So we have 2 times 2 times 2 times 3, right? And so we can only take 2 at a time. So we take our 2 there, we bring it outside, and these 2 are left in. It's because it's square root. Right. Yeah, if it were a cube root, then we could take all 3 of them and pull it out. But since it's a square root, we're only taking 2 of them. But that was a really good point, though. Glad we were able to get into that. Does that make sense to everyone? If it was a cube root, it would be different. Yeah, exactly. Awesome. All right. Let's do some more, and then we can get into some more fun stuff. Anyone want to help me out here?
May I try?
Sure.
It would be 1 because 1 times 1 is...
Perfect. Yeah. 1 times 1 is itself, and so we pull it out as 1. What about this one?
So it can be broken up into 2 times 6 or 4 times 3, which is easier to do since there's a square root in 4 times 3, which means you can automatically get something out. So it is 2 times square root of 3.
Perfect. All right. What about this next one?
May I have
The
a go?
next one, oh, sorry.
You can go ahead.
Okay, well, the next one can be broken up to 4 and 2, and you can automatically take out, well, you can automatically take out 2 because 2 times 2 equals 4, and well, it's not a cube root, so it'd be 2 times the square root of 2.
Perfect. Yeah. All right, we got 3 more here. You want to get on the microphone? This one is 10. All right, do you want to get on the microphone, explainer, or you don't have to if you don't want to? But you're
10
right.
times 10 equals 100. That's
Perfect,
all
yeah.
you need to know.
Yeah, yeah, you're good. So 10 times 10 equals 100. There's 2 of them under the radical, so we can pull that out. 10. All right, what about this one? It's a big number.
Can I have a go?
Sure.
All right, so 100, well, first to start, we already know that 10 times 10 is 100, correct? And if you multiply 10 by 100, you get 1,000. So if you simplify all of them, then it would be 10 times 10 times 10, correct? So then you will have 2 10s at the left of the square root, correct? And a 10 inside the square root. So it will be 10 multiplied by the square root of 10.
Perfect. Nice. All right, last one.
Can I go?
Sure.
So the easiest way to do that is to do 25 times 2, because 25 is a perfect square and can be easily square rooted. So it's 5 times square root of 2.
Awesome. Cool. All right, how's everyone feel about this? And you all got that really fast? All right. People feel great about it. Awesome. All right, now into the fun stuff. We could actually do some Pythagorean theorem. So this is really cool. It's about right triangles. So we're talking about the length of the triangle. So the square of the hypotenuse is equal to the sum of the square of the other two sides. So you see how this is the right angle here? So if we're looking across from this angle, the side that's not touching this angle, what's this side called? What's so special about this one?
Can I say it?
Yeah,
It's the hypotenuse.
perfect, yeah. So the
It's,
hypotenuse is always the longest.
Nothing, I was just saying that the hypotenuse is along the side of the triangle.
Perfect, yeah. So across from the angle, we have the hypotenuse, that's gonna be your longest side. So that's why it's kind of distinguished in this formula. Because see how A and B, they're added together, so they're kind of interchangeable. We could write B squared plus A squared equals C squared. And so like A and B can be switched around, but C has to stay in its place because that's the hypotenuse, that's the special side of the triangle. Like we want to make sure we know what that one is. Minus, oh, I'm seeing people rearranging the formula. That's awesome. Yeah, because if we want to get a side length, I'm seeing A squared equals C squared minus B squared. Yes. Then B squared equals C squared minus A squared. Seeing this in the chat, that's all great. Because yeah, we can solve this equation right here for each of these lengths. We can solve it for A and B and C. So in case we know like two of these sides, we didn't know the third, we can always find the third angle. So I actually have this on the next slide. Let's go there. Yeah. All right. So we got our formula, A squared plus B squared equals C squared. And we just did on the last, someone pointed out in the chat that A squared equals C squared minus B squared. That's awesome. But we can take this a step further, right? We can take the square root of both sides. So it's the square root of A squared equals square root of C squared minus B squared. And since we have that square root of a squared right here, then that would just be A, right? Because that squared cancels out the square root. And so then we have these formulas over here. A equals the square root of C squared minus B squared. B equals the square root of C squared minus A squared. And in C, it's just the same formula here, but we just do the square root of both sides. So how does everyone feel about these formulas? Does people feel great about them? That's awesome. All right. All right. Well, maybe we should, let's see, let's clear these. All right. So let's do some examples. All right, so everyone want to take a shot? Oh, sorry about that. Anyone want to take a shot on this first one? Anyone wants to get on the microphone and explain this one. So I'm seeing people, I see people in the chat saying that they have some more examples, and I like those. We're actually going to get into those later, the Pythagorean triples. Yeah, we're going to talk about those. But does anyone want to solve this side? Find this side.
So can I get a shot?
Sure.
So we know that 15 is a hypotenuse. So we know that C equals 15. And let's just say B equals 12.
Okay.
So the formula is A equals square root of C squared minus 12 squared, 15 squared minus 12 squared, which we don't, since they're the same, since they're being exponented by the same degree, we can just do 15 minus 12, which equals 3. And then we can do 3 squared, so 9, I think. Maybe 3, I don't know. I'm pretty sure.
Let's see.
Maybe,
So,
I don't know.
well, I think we can work this out, right? We have 15 squared, and that is 225, and 12 squared is 144. And that's going to be equal to the square root of 81, which is equal to 9. So yeah, this side missing here is 9. So thank you. That was great. And you want to get on the microphone, help me out with the next one? Different ways,
May
yeah.
I try?
Same answer. Sure.
So for this triangle, we already know that the hypotenuse is 15. So 15 is going to be C. And for 8, we can just do an A or a B. But I'm going to choose 8 as an A. So we can do.
Sorry to cut you off, but I just want to say real quick that our hypotenuse is actually the side that's across from the right
question
angle.
mark. Yeah.
Yeah.
All right. So then, okay, my apologies. I just noticed that. So for this case, 15 plus 8 would be 23. And 23 would be the hypotenuse for this triangle.
So our formula is C squared equals A squared plus B squared, right? And so we want to factor in the squares and the square roots. And so we have C equals the square root of A squared plus B squared. So we can plug in for A and B, right? So like, doesn't matter which one I call A and which one I call B, because they're interchangeable. 8 squared is 15 squared. And what's that? What's 8 squared?
64.
Perfect. What about 15 squared?
225.
Perfect. All right, I'm gonna add these up. And that would be, I'm gonna go up here.
289.
Perfect. It's 289. And what's the square root of that?
That is 17, I'm pretty sure.
Perfect, yeah. Equals 17. All right. That was a pretty crazy one. All right, we got some big numbers there, but it worked out. All right, what about this last one? Anyone want to get on the microphone, help me out?
1 squared plus 1 squared equal, or 1, so we know A and B equal 1.
Mhm.
So it's 1 squared plus 1 squared, which just equals 1 plus 1, so 2.
So we want to make sure we keep factoring in these squares and square roots, right? And so we have that C squared equals 2. That's right. But we need to take the square root of both sides, right? The square root
So
of
what? No, no,
so
no. Yeah, I have no idea.
yeah, yeah, it's not going to be a great number, so we can just leave it as the square root. Square root of 2 is going to be 1 point something, because we know that the square root of 1 equals 1, and like the square root of 4 equals 2. It's, you know, 2 is kind of in between these two, somewhere in between those two. It's going to be, square root of 2 is going to be somewhere in between. Oh, I got it. Exact answer, 1.42, and we're just going to continue that. All right. 1, 4. Is that a 1? Yeah. Cool. Same people in the chat. All right. So how was that? Used a calculator? Perfect. Yeah, I have my calculator right here as well. Always great to have it right there. All right. So that was Pythagorean theorem. We can do some cool stuff with it though. Let's look at that. So I saw someone in the chat kind of mention this earlier, but they didn't call it by name. Pythagorean triples. So hold on. I've got part of my screen blocked by the chat. So I'm gonna move you guys over here. There we go. A Pythagorean triple is 3 natural numbers, which are arranged from the smaller number to the larger number and form the sides of a right triangle. So if we had a triangle like this, oh, that's an ugly triangle. My apologies. Let's redraw that. We have a
Consider
triangle.
quadrilateral. That triangle that you drew because there's a side there.
Yeah, that's true. That's very true. Okay. So if these are my sides, A, B, and C, let's say that A is the smallest side. Then the triple could be A, B, C, because my smallest, hypotenuse is always the largest, and so the B just kind of, it's in the middle there, right? So the easiest triple is 3, 4, and 5. And so if I have triple, hypotenuse is 5 because that's the longest side, and then we can just call 3 and 4 either 1 because my drawings are not going to be the scale as much as I'd like them to be. Because we have the hypotenuse is going to be this number, and the side length, the legs of the triangle are going to be these guys. There's also 6, 8, 10. So yes, yeah. Let me clear this real quick. Make a very good point. I'm going to be talking about that in the next slide. So let's go there. So yeah. Multiples of 3, 4, and 5. Perfect. So yeah, any multiple of the triple is going to work. So we said 3, 4, and 5. And if you multiply that by 2, you get 6, 8, and 10. And that's still going to be a triangle. It's still going to work because you're just scaling your triangle by a factor, right? So if I have a triangle and I just make it a bigger triangle, it's still a triangle. And so that's why it works. So I think we multiply by 2 here, 3 here, and 4. So it's just this one, but you know, multiplied by a different factor. But they don't have to be multiples of this triple. They can be other things too. Like we have 5, 12, 13, and then 7, 24, 25, 9, 40, 41, 11, 16, 61. And there's stuff like that. Does anyone see a pattern here? Any patterns that they'd like to point out?
So,
Oh, you're good. You wanna point on a pattern?
sorry, my computer. So the each time the first number is +2, and then each time the second numbers are adding are by the same number. So 24 minus 12 equals 12, and 25 minus 13 equals 12. And same thing with, and then on and on and on.
Oh, I see what you're saying. Yeah, that is a pattern.
So it can be like +2, and then so like 5 to 7 is +2, 12 to 24 is +12, 13 to 25 is +12. So the last two will always equal the same to the next one.
That's really interesting. Yeah. So that is a pattern, and I like that a lot. What about a pattern between the numbers, like not going down, but going this way? Like a pattern between 5, 12, and 13, 7, 24, and 25, stuff like that. You can see a pattern in those.
The second two numbers are always adding by 1.
Perfect. Yeah. So we have +1 between B and C. B +1 is C over here. That's perfect. Yeah, because that works, right? Because 12 plus 1 is 13, 24 plus 1 is 25, and so on and so forth. Can we get B and C by just A? Yes. I see someone saying yes. Do you know how? No. Okay, that's all right. Well, let me tell you all. I just wanted to hear all your pattern finding skills, because I know that's my favorite part of mathematics, is finding the patterns. All right. So as who pointed it out? The last two numbers differ by 1. So that's true. We have this right here, tells us that these numbers, we have 4, 5, 12, 13. Perfect. But here's another interesting thing. I'm trying to rearrange my screen so I can actually see it. There we go. The sum of the last two numbers is equal to the square of the first number, right? So 4 and 5, or the sum of the last two numbers, right? So let's add these together. 4 and 5 is 9, right? That's the same thing as 3 squared. 12 plus 13 is 25. That's the same as 5 squared. That's a pretty crazy pattern, right? I think that's pretty awesome, because it keeps working. Whenever we do it for any of these triples that we're given, we can follow, it follows these two rules. So let's see. Yeah. So let's see. And also square divided by its 2. Let's see, a square divided by 2 is between B and C. Yes. So we take 3 squared, that's 9. Oh, lost my pen for a second. 3 squared is 9. 9 divided by 2 is equal to 4.5, and that's between 4 and 5. And that keeps working, right? 5 squared is 25, divided by 2, that's 12.1. And so we know my next two numbers are going to be 12 and 13. I'm just trying to make sure this is all in your heads, because the next slide, we're going to build our own triple off of just the first number. So how do you feel about this? How do we feel about building one of these? Feel good? All right. All right, well, let's do it. Clear this. All right. Okay, so we're gonna build our own triple, starting with 13. Our first number. Does anyone get on the microphone and explain how they would do this?
Can I?
Sure.
Well, I guess first it says like this 13 would be A. So I feel like I'm gonna square it into 169. And then B is, so B plus 1 plus C equals 169. Like or B plus 1 plus, because C is just like B plus 1, so I'll just do like 2B plus 1. Like 169 equals 2B plus 1. And then I subtract 1 from both sides.
Okay.
Now it's 168 and 2B. And if I want to find B, then I just divide both sides by 2. And B equals 84. And C is 1 bigger than that, so it would be 85.
Wow. I love that. Because that wasn't the way that we were doing it earlier, but it worked. Like, you got to the correct answer. Yeah, it'd be 13, 84, and 85. That was really good. That was a really interesting way to do it too. How else were we able to do this? Did anyone else use a different method for this?
I did a similar method, but it is different. So I started the same, 13 squared equals 169. I did 169 divided by 2, which equals 84.5. So then I did that minus 0.5, which equals 84, which was B, and plus 0.5, which is 85, which is C. So 13, 84, 85.
Oh. Yeah. So different methods, but it still worked. We got the exact same answer. All right. Anyone else have any other methods?
I did a similar method to Naomi. So I did the same with 169 divided by 2, which equals 84.5. But instead of adding like 0.5, I just took the numbers that 84.5 was like between, like 84 and 85. So B would have been 84 and then C would have been 85. So something
Nice.
similar, but not quite.
Yeah. Yeah, very similar, but we all got to the same answer. I think that's just like one of the coolest things about math. All right, well this concludes what I have for you guys. Let's see. Yeah, so this is, I'll make clear this real quick. Yes, so this was the method that was here. We started with 13 being the first number, and we square it, divide by 2, and then I think this is method when it was 84 and 85. Same as Naomi, kind of, it was just adding or subtracting by 0.5, but I like Ryan's method a lot because it was so different and very interesting. So very glad we got this. Right. Yeah, that's what I have prepared for you guys. Dr. Kwon, I'm not sure if you want to say something.